It's been around for a while. And I suppose, does this say it? Yeah, so in fact, some of these FQHE fractional quantum Hall effect systems are conjectured to host anionic qubits at certain parameter values, although that hasn't been demonstrated conclusively.
Are anions particles?
Yeah. So I guess yeah. So okay. So what's the way of thinking about it? An anion is Okay. So I can go a whole lecture on this. It's sort of like what you do is you create. So an electron is a particle, right? Okay, that's all I know. A proton is a particle too, except it's not really, because it's made up of smaller things, like they're called quarks, I think. It's made up of 3 quarks and it's all mixed up. And so one can imagine that there's even like there's a lower level system that in turn creates these electrons as sort of excitations of this lower level system, or these quarks of this lower level system. And so the idea of these anions is, or even of these fractional quantum Hall effects, is you create an interesting system. These are going to be planar systems. So you have some conductor here is surrounded by insulators on both sides. So you trap the electrons in a plane. And if you have exactly the right density of electrons, that's why it's called fractional quantum Hall effect. The fraction is the density, roughly. Then you can make the ground state, the physical state of the system turns out to be some very interesting, highly entangled state. So the electrons aren't sort of individually bouncing around like in a metal or something. They're not orbiting atoms like in a insulator or something, but they're highly entangled in some nasty way. And then the excitations above this ground state are you can think of them as particles, but they're made up of electrons. And so for example, in these FQHE systems, the excitations, even though they're made up of electrons, the excitations can have fractional charges. So you can have one of these excitations can have charge 1/2, whereas any electron has charge 1 or 2 or 3. 2 electrons will have charge 2, 3 electrons will have charge 3. But in fact, in these when they interact in this very complicated ground state, you can come up with an excitation that's charge 1/2. So you can think of this as it's not a fundamental particle because it's made up of electrons, but it is sort of an artificial particle in some sense. Yeah. I don't know. That's a very high-level picture, I guess.
So why is it theoretically shown to have better error rates?
Oh yeah. So the idea there is this. I guess both of these were sort of so anion refers to the fact that there's bosons and there's fermions and anions. So ani means 80. So a boson, when you switch 2 of them, you leave the sign of the wave function unchanged. So the wave function is symmetrical under interchange. Whereas a fermion, like electrons, the wave function is antisymmetric under exchange. And one can argue that that's the only possibility, because if you take 2 particles and you switch them twice, you got to come back to where you started. And so you either pick up a 1 times 1, or you can pick up a minus 1 times a minus 1. So you should come back to where you started. So you only have bosons and fermions.
So imaginary number?
But for anions, what we do is, if you have particles in a plane, that's not true anymore, because if you switch a particle once and then you switch a particle a second time, so if I have 2 particles and I swap them like this once and then I swap them like that a second time, they don't have to go back to where you started, because now in 2 dimensions, so in 3 dimensions if you do this, topologically swapping them twice is equivalent to doing nothing, because you can continuously deform this into this and this and into which you're not doing anything at all. But in 2 dimensions you can't do that, because if you send one particle around the other, there's no way of topologically deforming that closely, so it's just sitting alone. And so possibly that is something different. And so that's why it's called anion, because not only can you have a phase of plus or minus 1, when you wrap one guy around another, you can actually have a complex phase or something. And even more interesting is you can actually have a higher dimensional space, and you can do it like an actual gate when you like a 1 qubit gate or something when you send one particle around another.
High dimensional space is it's not 2D anymore.
Well, so if all I had was a bunch of electrons, then the ground state would be one dimensional. It would be some antisymmetric state between all these fermions. But when I have a bunch of anyons, the ground space can actually be higher than 1 dimensional, so you can actually put information into it. And then when you wrap one particle around another, that's called braiding. You apply non-trivial quantum unitaries to the ground space. And so this is okay. So it's called, this is topological because the way you do operations is you send one guy around the other guy. You braid them. Okay, and that's also sort of why people think that it might be potentially maybe lower noise rates, because it's not like it's a different kind of operation, right? So if you have an atom like this and you shine laser light to drive a transition between these two levels, you're sort of always going to have some sort of level of noise, because you won't run, the laser will be sort of off, you won't run it for the right amount of time, who knows what any number of things could go wrong. So you'll just be off by sort of like epsilon, and your goal will be to make epsilon as small as possible. But when you do these kinds of operations, when I have a two-dimensional ground space and I send one particle around another, like that, there's no reason that you can't have epsilon errors, because the operation comes from the topology of the diagram. As long as you keep these particles separate, I mean, if the particles are collided into each other, who knows what happens? But as long as you keep them separate from each other, the operation we say it's topologically protected, because there's nothing close to it that you can get to. That's the idea. Basically, people expect that the error rate should drop exponentially as the temperature goes to 0. So if you keep it at a low enough temperature, the error rate should be reasonably low. But this is a really active area of research, exactly understanding what the error model should be, and what the error rates will be, if it works out at all. But there's some hope. And that's cool. I mean, it's cool that there's substantial resources being looking into this, because it's good physics, if nothing else. I mean, it's really cool to think about these fractional quantum Hall systems, or these analytic systems, or these topological insulators. It's pretty interesting that you have the ground states are these extremely interesting entangled states. Okay, so what do I have here? Right, so I obviously just stole this from these pictures. Right, so this just explains, for different kinds of technologies, NMR, ion traps, and so on. It gives you some sort of comparison between them on different interesting parameters, like decoherence time. That's the lifetime of your qubits. The gate speed is important in practice, and so on. Sorry?
Anyone is not there in the list.
Well, anyons don't exist, as far as we know, but maybe they will.
So whatever work that right now is going on is just theoretical.
Well, I don't know. I mean, if you look at you can Google up things where they give they're fairly open about at least some of their expected details. So let's see. I think, let's see. So this is from September 2019. Optimizing Clifford J generation. Yes. So if you click on one of these papers, you can sort of see the parameters that they're looking at. So this is Microsoft Station Q in Santa Barbara, and Microsoft Quantum in Redmond. Right. So they go into a fair amount of detail. This is their architecture. So each of these are superconducting wires, topological superconducting wires, whatever that means. Fancy. This is a superconductor, and so this I don't know, I could explain this if you care, but I should give a lecture then. So this is called an island, and it has six of these anyons on it, and that gives you a 4-dimensional space, so that gives you actually 2 qubits.
Is this a model or it's like experimental set?
Oh, sorry, yeah, this is supposed to be experimental, so this is supposed to be, it's not to scale, but this is supposed to be the top of a 2-dimensional picture. I think these directions are much longer than this direction. Maybe these wires have to wrap around or something because they're too long, but something like this. And the way you do operations is you turn on and off interactions here, so these are gates. And they probably talk about the noise rates even. So they have pictures on the different geometries they're considering. I don't know what else they have. What was the question? Just.
I was just curious, like experimentally, what exactly has been done in this field?
Yeah. I'm not really sure because, like, recently, since they've all gone to work for Microsoft, I don't actually know. Like, I don't think they're publishing at the same rate they were before. It's hard to say because, especially like when you talk to them, I don't think you really get like the straight answer because they're always extremely optimistic. So for the last couple of years, they've been saying, "Yeah, we'll see it by the end of the year." So obviously we haven't seen it by the end of the year for the last couple of years. I doubt that we'll see it this year either. But I don't know what the problem is really. What the holdup is. Obviously they're having some problems.